In Scenario 3 of ClusterXL troubleshooting, we are using in our 77.30 load-sharing ClusterXL, in Unicast mode, and same version of security management. We will demonstrate advanced troubleshooting of a traffic problem. In this scenario, there is a problem with FTP connections, which are going through the load-sharing cluster. The FTP connection from the client opens, and authentication is successful. But after that, the connection hangs, and no data can be received. Searching the Smart View tracker for FTP connection does not show any drop. In order to troubleshoot this issue, we want to collect relevant information from the cluster gateways. In case of load-sharing cluster, the connection can go through any one of the gateways, so we want to collect the information from them on the same time. When collecting debug information, there are several important points that we need to consider. First, the debug information has to include relevant data on the issue. In order to obtain it, we will start the debug, replicate the issue, and stop the debug. Second, in case we collect information on more than one gateway, it has to be done exactly on the same time. And third, to help us find the information in the debug output, we have to focus on a specific connection that is failing, and know its source IP address, destination port, and the firewall interfaces it is going through. In our case, we want to run the same debug on the two cluster gateways on the same time. To make it easier, we will automate the process with a debug script. The debug script is a text file, with a .sh extension. On the top we specify the shell executable that we are using, bash in this case. The echo statements will output messages to the screen, or to a text file, which we will receive with the output. The next two lines will run TCP dump, on the incoming and outgoing interfaces. The % is used to run the command in the background, so the next lines of the script will be executed. Here we run FW monitor, with a filter on the client and the server IP addresses. Next we are running a minimal set of kernel debug, to see kernel logs, drops and decisions regarding the connection. An important note is that running the debug commands in the script can cause some extra load on the security gateways. It is highly advised not to run it on normal working hours, but during a predefined maintenance window. Next, a message will appear on the screen, that the debug will run for 30 seconds. This is the time in which we have to replicate the issue. After 30 seconds, the script will stop the debug. First it stops the kernel debug. Then kills the TCP dump, and the FW monitor processes. It then zips all the output files to one tar.gz file, cleans the temporary files, and writes the output file name and path. Next step is to transfer the debug script to a folder on each one of the cluster gateways. Open SSH consoles to the two gateways. Browse to the directory where the debug script is located. Change the script file to Unix format with the DOS to Unix command. Give it executable permission with the chmod command. Now we can get ready for running the debug session. On each one of the gateways, type the command to start the script, but do not press enter. Open the client and type the command, which will replicate the issue. Don't press enter yet. When ready, press enter on each gateway session, and check that the script starts. When we see the debug running message, change to the client and run the commands which replicate the issue. When the problem is replicating, move back to the SSH console. Verify that the debug was running when the problem happened. Check that the debug files were created, and move them to your workstation for analysis. A point to verify on the cluster, as this is a load-sharing cluster in unicast mode, is which member is the pivot. In contrary to load-sharing multicast cluster, in which all members see all the packets, and decide which member should handle each packet according to an LS algorithm, in unicast mode all the packets are arriving to the pivot member, which handle 30% of them, and send the other 70% to the other member. In this case member GW1 is the pivot. On your workstation, extract each output file in a different directory. We examine member GW1 output files, and start with the packet capture files. We can see that the size of the FW monitor output is 0 byte. This means that the packets matching the FW monitor filter expression did not go through GW1 firewall chains. This happens because the pivot member forwards the packets to the non-pivot member on layer 2, the network layer, before they reach the application layer. Let's open with Wireshark the TCP dump from the client side. We apply a filter of the client and server IP addresses. We can see the FTP SYN packet on port 21 from the client. To verify on the different files that we examine the same connection, notice that the source port is 1472. The SYN packet is not here, but it doesn't mean it was not sent. We can see the client sending username and password, and then sending the port command to request to open a high data port. And right after that the NLST command to name list of the FTP directory. Next we open the server-side TCP dump capture, and apply the same filter. Here we can see the missing SYN packet. Notice it is the same connection. The server request for a password, welcome message, and user login. This is the server response to the port command. Then the server is opening a new data connection, and there it stops. Now we want to open the files of the non-pivot, GW2, which actually handled the traffic. On the client side we see the same flow of events. Please notice that this is the same connection. The last packet is the client ACK to the server's message that it is going to open a data connection. On the server side, the last packet is the send of the new data connection, on port 20, from the server to the client. Let's open the FW monitor capture on GW2, and apply the same Wireshark filter. In FW monitor output we see each packet printed 4 times, as it passes through the firewall chains. Little I and capital I are before and after the inbound chain. Little o and capital O are before and after the outbound chain. Notice that this is not the same connection we have seen in the TCP dump. but a previous one, as the source port here is different. Browsing a little down, we can see the connection with source port of 1472. Checking the data connection on port 20 just before that, we see it only in little I, before the inbound chain. This means that this connection was dropped by the firewall. The FTP protocol uses different connections for control and for data, similar to H323, RTSP, and other protocols. With these protocols, on the control connection the client and server agree on a dynamic high port, which will be used for the data connection. This high port is not opened on the firewall rule base. For this the firewall is using an inspect code, and when it identifies a new connection on one of these services, a custom inspect code is executed, and dynamically accept the new connection in the high port. But this is not working in our case, and we want to find out why. It is time to open the kernel debug output. This output may look hard to follow, but it can be read in an intuitive level. The important point is, in order not to get lost, is to search the specific connection, which you identified in the capture. First we look for the data connection. Server IP, followed by a colon, and 20 for the port number. FWCon lookup is the kernel looking for the connection. Here it enters the virtual machine inbound chain. Here the rule base returns drop on rule 30, which is the cleanup rule. This drop means that no link have been created from the control connection to accept the data connection. We go back to the top and look for the control, port 21 connection. We verify the source is our client. We see here it is a first packet of a new connection, as it is not found in the connection table. It enters the VM inbound chain. It is processed, and a link is created. The rule base accept this packet, on rule number 4. Let's open the smart dashboard and check rule number 4. We can see the relevant networks on the source. On the service column, there is a custom service named MyFTP. Opening this service, it is TCP port 21. And on the Advanced tab, there is nothing selected as the protocol type. The protocol type is what notifies the firewall to execute the custom inspect code when it identifies the related port number. We select protocol type FTP and install policy. After policy installation completes, we return to the client and test the FTP connection again. The user authenticates. The ls command does work. And now we can download a file. To summarize this session, in order to troubleshoot the FTP connection issue, we used a debug script to collect packet captures and kernel debug. Started the script on the same time, on both cluster gateways, while replicating the issue. To analyze the files, we started with the packet capture, to understand the packet flow. We identified and focused on a specific connection, and searched it on the different files. Then we compared the expected connection behavior to our findings, in order to understand where the failure is. And finally, we cross-checked the troubleshooting findings with the security management information, and found the reason for the failure. Thank you for watching this video.